Hello everyone. I am Beth Kemani, the AI ML track lead at Google Developer Group's Chuka University. And today we're going to talk about the art of feature engineering. And so we often hear that data science is 80% data, and that is data preparation, and 20% modeling. Yet we go into conferences and we spend 99% of our time talking about the 20%, that is the algorithms. So today we're going to change that, and we are going to talk about the 80%, and we are also going to talk about, and that is what we call feature engineering. So in machine learning, in machine learning our model in a machine learning model, like a world class chef, even the best chef in the world can't make like a 5-star meal out of rotten ingredients. So feature engineering is the process of selecting, cleaning, and transforming our ingredients so that our model can actually extract a signal from the noise. So if our data is messy, our model isn't learning, and it's just memorizing garbage. So let's delve in. So uh, we're going to talk about the pillar, and that is handling missing values. And first thing you'll encounter in real world data set as a whole is an NaN, or a null. So in a school, they give us perfect CSVs, right? But in real world, we have sensor fails, and users skip questions, and the database becomes corrupt. So before you write a single line of code, you have to ask, why is it missing? And if it's missing completely at random, that is the MACR, like a random glitch, we can usually just fill it with a mean or median. So but what if it's missing not at random? So that is the MNAR. So imagine a survey about mental health, right? And people with high anxiety might be less likely to answer a question about stress levels. So if you feel that silence with the average stress levels of everyone else, you have just deleted the most important signal in your data. So, and in those cases, we often create missing indicators. So, um, we usually create missing indicators, and a new column that says one if the value is missing, and a zero. Okay, one if the value is missing, and zero if it isn't. So sometimes the absence of data is the data. So yeah, so as you can see in slide 5, as you can see here, we will use a simple imputer. My professional, we will use a simple imputer, and my professional advice is always default to median. So the mean is easily bullied by outliers, and if you have 1 billionaire in a so if you have 1 billionaire in a in a room of teachers, the mean income suggests that everyone is a millionaire, right? And the median stays grounded. So yeah, we shall write this code, so don't you worry. But we have to move to the categorical encoding first, so that we can go into hands-on. So now we move to the language barrier. So computers are essentially great calculators, right? They love numbers, and they're confused by New York, and they're confused by, say, New York or Paris. So we have two parts here. So, and we have one is one-hot encoding. I think you're familiar to that because it creates a new column for every category, and it's the fair way to encode. It tells the model that Paris is not greater than London, and they're just different. But we do have a danger zone, and that is the trap. It is the curse of dimensionality. And if you want to encode 500 different zip codes, you just added 500 columns to your spreadsheet, and your data becomes sparse. So imagine you're trying to find a needle in a haystack, right? Difficult. But every time you add a column, the haystack gets 10 times bigger. So yeah, that's the mess. So we also do have the ordinal data. So and the ordinal data is where we add and the ordinal data is where order matters, like small, medium, and large. So we use label encoding. So um, yeah, so we use label encoding, and and we assign them 1, 2, and 3, and this preserves the mathematical relationship. So if you use one hot encoding in an on educational level, you're throwing away the information that a PhD is more education than a high school diploma. So do not throw away your domain knowledge. Great. So uh, Um, another thing in feature engineering is scaling and normalization. So this one, perhaps it is perhaps the most overlooked step, because imagine you're predicting health outcomes, right? And you have a column of age, and the age runs from 0 to 100, and you have another column of annual income, and the annual income varies from $0 to $1 million. So many algorithms like KNN or SVM, that is standard vector machine, or even neural networks calculate the distance between the data points. So if you scale your data, the model will look at it will look at the say $110,000. We look at say $10,000 difference in income, and a year difference in age. So, and it will conclude that income is $10,000 times or more important. So it's a mathematical hallucination, right? So yeah, and then in terms of normalization, so in terms of normalization, it can also be called min max scaling. And what I mean by this is normalization squashes everything between 0 and 1, and we use this you use this when you need a hard boundary, like say in image processing, and standardization, which is also the z-score. It just centers your data around 0 with a standard deviation of 1. Okay, we will understand all this when we get to hands-on, and it is and normalization and standardization are more robust to outliers. And if a data point is like 3.0 after standardization, you know it is an extreme value. So it is an extreme value, that is 3 standard deviations from the norm. So yeah, I think we shall. This is what I was talking about in normalization. So so if you look at the code, if you look at the code, you're able to notice that we scale after we handle missing values. So order of operation matters in feature engineering just as much as it does in algebra. Okay, so yeah, give me 1 second. So yeah, in conclusion, I do have a golden rule, and we have actually covered a lot. But if you remember one thing today, let it be this. Data leakage is the silent killer of models, and never ever calculate your scaling parameters like the mean or the max using the entire data set. So you must split your data into training and testing sets first, and then you fit your scalar on the training data only, and then you transform the test data using those same parameters. And if you use the test set mean to scale your training data, your model has already peaked at the future. So it will look amazing in your lab. So, and if it will fail, and it will also fail miserably the moment you put it in front of, say, real consumers. So feature engineering is where you turn a library of raw facts into a story the machine can read, and this is why you respect data and understand the why behind the numbers, and your models will reward you. So I think we should just delve into the hands-on, but that is basically the nuts and bolts of feature engineering. So yeah, let's move into the nuts and bolts. So we shall start by handling data. So just give me 1 second. So yeah, first we shall start by importing the relevant libraries. So we're going to import pandas as PD, and then from scikit-learn dot impute, we're going to import simple imputer. So let's just do that. and then we shall try to sample data. So what we're doing here is actually sampling data. Sorry. So we should give it the variable. We should give our variable name as df, and then we just say pd dot data frame. We're going to use the same age. Sorry. Then we just give it a list of, just say 25, then 30. Then you can read a CSV file or an Excel file. I just want to make things easier. And 35. Yeah, so there it is. So let's run that. So we shall do the mean imputation. So and in the mean imputation, this is where we like get the imputer. We create a variable, name it imputer, and then we do a simple imputer, and then we try to fetch transform. So yeah. And then we shall do a df of age. So we should do, yeah, an imputer transform, and then df age. Yeah, so let's see how that goes. Great. So we should try to drop a few rows. So dropping rows. Once again, you can use your own data set. So you're not confined to using what I'm using. So you can just load your own. So yeah, that is it basically. So we have handled missing data. So if we read there, we actually have the 25, the 30, and the 35. So yeah, that is how it is. So we are going to move into one hot encoding, and this is where we let's see if we can use like a more concrete data set. I think I have one. Oh, no. Yeah, I think I just have to paste this.